Hi, I'm Chris Brown, and this is the Module 2.11, an intermediate axiomatic design. It's part of a course on axiomatic design in manufacturing processes at WPI, where I'm a professor in mechanical engineering. So in this module, we're going to present a brief summary of what's been done in Section 2, take a brief look at innovation and the value chain. So the sections, topics in Section 2. So one of the most difficult things is doing decomposition. So we took a careful look at the FRs and the theme selection and C-mean, decomposition techniques, classification of procedural errors, in FR definition, CNs for the requirement process, kinds of coupling. So all of these first ones relate to the decomposition and forming that. Then these relate to axiom 1. They're essentially these four, and this one is just about developing the equations, which also relates to axiom 1. So how to develop a good decomposition is one of the main points. How to work quantitatively with axiomatic design, we're starting on this. Because if you just know the axioms and you don't have the ability to develop a good decomposition and work quantitatively, you can really only solve the simplest of problems. So the decomposition and creating a good decomposition is, as I've said before, is probably the main impediment to using axiomatic design. And so learning how to do this is key. So we've emphasized the use of themes, which will help to make sure that it is design is collectively exhaustive and mutually exclusive, and we have the minimum number of FRs. It's also important to be able to recognize good FRs, DPs, and PVs, so we spent some time doing that. And we also want to be able to recognize a constraint and tell a constraint from an FR. Professor Thompson has talked about the differences between FRs and non-FRs, and selection criteria and optimization criteria. So we spent some time in that. Thompson has also written about stakeholders and developing of requirements, and we've applied that in a couple of ways. I've spoken about the inheritance of coupling from children to the parent, so we can see what the impact is on the full impact is in the design matrix. And also spoken a little bit about how to recognize coupling and how to rearrange design matrices to decouple designs. So also we're going to talk briefly here about relations between axiom 1 and 2 and innovation. So axiom 2, let's take another look at this. So axiom 2, we're trying to minimize the information content, and the information content can be defined as the log of 1 over the probability of success. So we might restate this axiom 1 to maximize the probability of success in fulfilling the FRs. That's essentially an equivalent statement to minimizing the information content. Although, as it turns out, this is an easier thing to do and has got a grounding in previous work on Shannon's information theory and Boltzmann's entropy. And I'll mention that in a later lecture. So axiom 1 is maintaining independence of the functional elements. And so we want the design to be adjustable and controllable and to avoid unintended consequences. These would all, lack of adjustability, controllability, and unintended consequences would all adversely impact the probability of success. So in some ways, axiom 1 is kind of like low-hanging fruit for axiom 2. So axiom 1 gets rid of some of the, let's say, easy things to do, the things that are clearly wrong with the design, that would prevent it from being adjustable and controllable. and lead us into unintended iterations. And in fact, it's this that leads us to a lot of innovation, and I want to emphasize this in the innovation part. So eliminating imaginary complexity can be a very easy way to eliminate, to innovate in an existing design. So you have to recognize that you're doing some sort of non-value added iteration with some sort of system, and then and to eliminate the imaginary complexity, as we've discussed, you just have to rearrange the matrix so that you can find an order of adjustment that does not require iteration. So if you don't know the order of adjustment, it can seem like quite a complicated system to adjust, but once you know it, it becomes very simple. So you've essentially found the combination to the lock. Recognizing the need for new FRs. So when you're using a design and you find that you're going through some non-value-added iterations. Now in manufacturing you might be trying to adjust a process so that you're getting good output, and if you find that you have to make some adjustment, measure the part, make some adjustment, measure the part, you may be missing an FR. And so when you have some sort of frustration with the performance, and I spoke about this in a previous lecture, where I was frustrated with getting stuck behind trucks and noticing the coupling between transportation systems for people and merchandise. So let's consider briefly as well value chain and cost reduction. So the value chain is established with the customer needs. And so as we look at existing designs, if we can establish what the customer needs are and get a good design decomposition, we can take a look at the elements in that decomposition and say, can these be tied back to the customer needs? So at the first level we're looking at the FRs, and then at the next level we're looking at the DPs and finally the PVs. So we may be able to extract cost from a design or a manufacturing process for a design if we can go all the way back to the customer needs and say, all right, what here is impacting the customer, what here has got a direct link back to the customer needs, so that we can see if it's actually adding value to the design, because if it doesn't address a customer need, either directly or indirectly, as some sort of, say, supporting sub-objective for the design, then we should look to see if we can eliminate that. Now, until we know how it's coupled with other things, or where it appears in the design hierarchy in the design matrix, it can't be safely eliminated because we don't know what the other interdependencies are. So one of the things that axiomatic design does as well, that I've mentioned before, it reduces design times. It assists in communication, and we know the design intent because it's linked right there. It begins with the design intent for the FRs. And much of the time in design reviews, without axiomatic design, is spent just explaining the intent, whereas that should be evident with the design, with the physical elements of the design. One of the things, too, that we can do with axiomatic design is we can focus the resources on the best design early in the design process, so that we can use the axioms to identify the best design solution still in the conceptual stage. And then we can focus our resources on what we know to be the best design solution, and therefore promote that more quickly than we would have if we were trying to investigate several, and perhaps put too many resources towards design solutions that we could have told would be unsuccessful had we applied the axioms. So this helps us also to avoid unnecessary prototype testing. As we looked back in the first part of the course, the conventional design or traditional design often has us doing prototype testing to see if a design is good. Whereas when we make the design matrix, what we're essentially doing is functional testing. We're looking to see how the physical elements are influencing the functional elements. So it's a kind of functional test that we can do before we actually make the prototype. So essentially, while we can focus our resources, we can also avoid investing in design solutions that don't work. Thank you for your attention.